Hello everybody, my name is Josephine Edery, and today we'll be discussing the 1987 radiological accident that occurred in Goiânia, Brazil. Before we begin, let's discuss some key topics we are going to review in this presentation. By the end of this presentation, you will learn more about a background on the Goiânia radioactive accident, an overview of the geographical details regarding the accident and its impacts, how soil sampling played a role in testing, the longitudinal effects of the accident, waste management strategies that were utilized, as well as key policy changes. Let's begin by discussing the source of the incident. In 1987, two men stole and then attempted to resell an unidentified piece of equipment from a partially demolished private radiotherapy institute, unaware that the equipment contained cesium-137, a radioactive isotope that emits gamma radiation. While the two men were in the process of stealing the equipment, damage occurred and the piece ruptured, spreading the cesium-137 in the form of cesium chloride salt. The two men sold the scraps to a local junkyard, where it was distributed within the community. This distribution led to severe contamination within the city, impacting both physical and environmental health. The rapid spread of cesium-137 had several physical and environmental health impacts. The accident led to both external irradiation as well as internal contamination, water, soil, and air pollution, 249 individuals exposed to the radioactive substance with 4 fatalities, economic deficits, as well as a large level of radioactive waste, prompting the need for increased space. Let's begin by assessing the source of contamination as well as the key contamination sampling sites. Here we have an aerial view map of Goiânia. I have circled in red the location of the junkyard where the scrap pieces of equipment were sold, located off of 15A Street. The surrounding areas included an additional junkyard as well as populated residential areas. As seen in the key, high levels of radiation were seen in the immediate surrounding areas. Now, let's assess contamination levels collected from key sampling points. While assessments were conducted on soil, water, and food, we will be assessing the levels collected from soil, as research showed little to no levels within ground and drinking water. Let's start by looking at some of the focus sampling sites. We can start by looking at the IGR clinic. This was the clinic the stolen equipment originated from, where radiation levels presented at 4.56 SVH. Next, we can look at the junkyard where the equipment was sold to on Rua 15A, where levels presented at 1.5 SVH. An additional junkyard on Rua 6 was assessed, where contamination levels presented at 2 SVH. Lastly, surrounding residential areas were assessed, presenting at 5 SVH. Other manned sampling sites included one of the thieves' homes where the source was dismantled, as well as additional junkyards. Next, let's assess some longitudinal data. Prior to delving into this slide, I want to share an interesting piece of information. 4 months prior to the incident occurring, the owner of the IGR clinic was unable to remove the radioactive material from the clinic due to police force sent from the administrative director at the Institute of Insurance for Civil Servants, who claimed he would take responsibility for any radioactive accident in the event of occurrence. Let's take a look at Figure 3 now to understand the long-term lifespan of the radioactive chemical impacting Goiânia. In 1971, cesium-137 levels within the clinic were reported at 71 TBq. Assessed again following the accident, TBq levels were at 50.9, with around 44 units of TBq being recovered in 1987, as well as 7 more unrecovered units. As sampling continued, 3.5 units of TBq were recorded in 2016. It is important to note here that cesium-137 has a half-life of 30.17 years, meaning after this time period, half of the original amount will have decayed naturally, showing the causation between long-term environmental and physical health effects. Now let's assess decontamination efforts. Due to large-scale contamination of cesium-137, large amounts of resources were needed to aid in containing the waste in a safe and secure manner. The packaging of waste required 3,800 metal drums, 1,400 metal boxes, 10 shipping containers, and 6 sets of concrete packaging. Today, contaminated radioactive waste from the accident is buried at a temporary site near the village of Abadía de Goyas. The site is a surface repository on the outskirts of the city where it must be isolated for the next 300 years to ensure no possibility of further contamination. Now let's take a look at some policy and regulation changes. The 1987 accident acted as a major turning point not only within Brazil, but internationally as well, as policies and regulation changes regarding radioactive safety were formulated and refreshed. Let's take a look at some of the enacted policies and their purposes. CNEN Resolution Number 6 was enacted in the year following the incident and required an updated inventory of all radioactive sources within the country. CNEN 6.01, enacted 2 years after the accident, required individuals handling and using radioactive sources to be trained and certified. CNEN 6.05, originally created in 1985 but reworked after the accident, created stricter guidelines for radioactive waste management, including the necessity for additional classification units and sorting strategies. Lastly, Law 10308, enacted by the federal government and enforced in 2001, created stricter responsibilities and required authorization for those handling radioactive waste. To close out this presentation, it is important to view the effects of this accident as a multi-level catalytic event, as many parties were and are still impacted by the destruction caused. By assessing current policies put into place as well as steps taken after the incident, we can formulate a strong framework for disaster preparedness as we address both the environmental and physical health effects.